This is Algebra 1, Term 4, Lesson 4, Optimization. First, we'll do a Desmos classroom activity, build a bigger field. Then we will do some work in slides, building a fence to enclose a pasture. And finally, we'll do a team task, similar task, but this time we're building a fence on the side of a barn. So let's take a look at build a bigger field. So this is our introduction to optimization. I don't really discuss that term at all actually in this lesson, so it might be a good idea to actually give them the definition of the word optimization. But that word is here in the directions or in your directions for this activity. It says we're going to optimize the area of a field with a fixed perimeter. And this is a classic application of quadratic functions. This has a total of 13 screens, but the last two, they call them extensions. I say, yeah, they may be two that you want to leave off or let them be extra because this is a very full lesson. I've scheduled this for 1 to 2 days, but I would say 2 days is probably about right for most. So let's take a look at our first screen. In this one, they're going to tell which has the largest perimeter, and they're just guessing at this point. And then they're going to start predicting, putting them in order by areas, like which one do you think has the largest area, which has the smallest area, and so they will arrange them. And then they're going to have to actually calculate the perimeters and calculate the areas. And then on this one, they're going to adjust these rectangles. They need 3 different rectangles, but they must have a perimeter of 50. Now see, mine says 60 right now, so this would not be acceptable. They can just move it around and tell them to make them all different, not to repeat the same ones. And then they will click on these buttons to build 3 different fields, field A, B, and C, using exactly 50 meters of fencing. Once they've done that, they will go over here and calculate these widths and these areas based on their particular model. So they will definitely have different answers here, and they should be calculating those based on their own answers. If students don't recall the area of a rectangle is length times width, you may want to do a quick review of that because they are going to be doing areas of rectangles pretty much through the entire assignment. So that's a very critical thing to know. I'm guessing most kids have seen it many times and already know it, but it would be smart to show them that. And let me show you an app that I've used to help with that. I will give you a link to this in your teacher notes. Now this is not technically part of this lesson, but if you have a lot of kids that really don't know what area of a rectangle means, then this might be something to let them play with and make sense of it. So the length is 8, the width is 6, the area is 48. Well, they can see 8 times 6 is 48. They can also count the squares, but each of these squares is worth more than, obviously these squares are 2 by 2, so 1 square in this case would be 4 square centimeters. But if you just need a model like this to get their minds wrapped around the difference between area and perimeter, that would be smart to help them with that. They do need that concept pretty much solid before they proceed through this lesson. So let's go back to building a bigger field. Once they've completed their table here, they're going to be graphing the relationship, and obviously this should create a quadratic. It's going to show little dots along the curve for these parabolas, and they will be different. They will pick the function family that best fits this function. They're going to place this dot where they think the largest possible area for this field will be. So this is our optimization where we find the maximum area, and that's where they're going to place the point at the vertex of the graph. Now when you get to this screen, this is where we're going to develop an algebraic expression for width, and then we're going to multiply together our algebraic expressions for length and width to get our algebraic expression for area. They do not need to distribute. They may leave parentheses in their area model, and I highly recommend it because it actually makes it easier to make sense in the context. So just leave those parentheses in there. This one tells you is going to give the graph of the function and then ask a question. I can't display that because I haven't worked the problem yet. And then these last two, you're going to be writing instructions for how to find the dimensions of the biggest field giving any length. So let's say we have 50 meters, 60 meters, or 600 meters, or m meters. How would you find it? So they could generalize that for any circumstance. This is a great task to do. I just don't know that I would throw it at them the first day. I think they might ought to come back to this. But if you want to do it, go for it. They do have some teacher moves and sample responses for these. And this one says, imagine you have 50 meters of fencing, but you're building along a wall. So you only need, so here you only need how much? Well, I can't do 50 here because I've already used up all my fencing for the length and I have nothing for the width. Now this one wouldn't be a bad one to play with because they're going to actually need this for their team task. So you may actually suggest to your teams, if they're struggling, go back to that extension number 2 on screen 13 in your task, and they can use this model to kind of figure out what they're doing for that task. So the first screen they are given is this one, and I've given them some scaffolding because I've actually entered some suggested widths in the table. Now I do start with a width of 0, and we should know that a width of 0 really is not in this context, because if there was a width of 0 on this enclosed rectangular area of a pasture, then we wouldn't really have an enclosure at all. So really 0 is not going to be included, but we do go ahead and put it in the data just because it makes it easier to see what's going on and see what's happening in the graph of the data. So you may suggest to them, just because 0 is not in the domain of the function does not mean we cannot at least look at the number 0 in our table and see what's happening. So if you have a width of 0, how much fencing would they have for the length? Now this gets into perimeter. My suggestion would be to give them pencil paper and have them sketch widths and lengths and try to make sense of the 240 feet of fence. If you don't use any of your 240 feet for your width, how much would be left for your lengths? And you have 2 lengths that are the same here. And then if the width is 0, then obviously the area will be 0 as well, which is why we don't really include this in our domain of this situation. Then let's try 20. So they'll notice I'm not counting by ones. But the reason I'm not counting by ones is I don't really want to count by ones all the way up to 120. And then the next question would be, why not stop at 120? Why don't we stop at some other number? So have some conversations about that as well. I'm probably going to have to make a second video thoroughly explaining these problems to you because this is challenging work for kids at this stage, very challenging. But I definitely expect them right up front as we study quadratics to begin these big application problems. And if you'll notice, we are tying in so many different concepts as we do these. So this is not only teaching them new concepts about quadratic functions, but we're also reviewing concepts of linear functions, rates of change, average rates of change, and so many more things, domains, and even whether to use counting numbers or real numbers for our domain. So here it's asking how are the lengths changing and how are the areas changing. Now we're going to extend that. I asked them to actually build a linear model for their side lengths, length of their field versus width, and then talk about the slope of that data and what does it reveal in this context. And then we're going to evaluate at a particular point. So let's say x is 50. If the x is 50, what's L of 50? What does that reveal in this context? And can the intercepts of the graph be included in this context? Intercepts being x-intercept and y-intercept. So have them talking about that, look at their graphs, and ask if does it make sense in the context of this pasture and this fence? Can we use those numbers in this situation, or are they outside the context that we're talking about? Then they're going to build another model with area. So the area will be length times width. Now I've given you an example of the equation. They do not need to use standard form of a quadratic equation here. They are simply taking their linear model that they've already written, L of x, and they are multiplying that by the width. Let's see, let's give them the opportunity to get it before you say anything. So do look at the teacher notes and the teacher guide for the expression that I have in your table for the area, and they will use that here. It's also asking what is a of 50 and what does it reveal in this context. Same thing, 50 is x, what did we say x was, and what is a of 50? What does that mean in this context? Then they're going to give the maximum possible area for the rectangular pasture. I did arrange the numbers in the table so that that would be obvious. Hopefully they already know that. If not, their graph will definitely show them the maximum possible area, and they're just looking for the highest point of that graph. I do have quite a few show notes, so let's take a look at those as well. So way back on screen number 2, I'm asking, are widths of 0 and 120 actually possible? So even though I included those in the table, let's talk about why that may or may not work. Then I tell them in these instructions down here to create a function for L of x, the length as a function of the width, and for A of x, the area as the function of the width, and they're telling them where to insert those on their slides. So when they come to their next slide, see, it's telling them to insert on this slide your function for L of x. Now what function family is represented by L of x? So again, we're covering many concepts here. When they get to screen 4, what function family is represented by A of x? Is there a lowest possible area? That is a very deep question. They may just, eyes may glaze over on that question, and it's okay if they don't get it. It's really okay. You can tell them there is no lowest possible area here because 0 is not included. We do not have 0 area, because if we have 0 area, we have not completed the task we were given, which was to build a rectangular area of our pasture and to enclose it with a fence. All right, when they get to this one, they're told to find the rates of change in their table. So this one, they are actually copying the table from slide 2. So they will come back over here and just copy this. So grab it there and click Control C, and then come over here, Control V, and just drop it right here on the slide, and then find these average rates of change between consecutive points. Now what I did is I actually typed these into my Desmos calculator and screenshot every little one. It may be quicker to give them a whiteboard and have them write the average rates of change between consecutive points in the table and insert those. And then I'm not asking for any specificity on this one at all, so don't let them spend too long on it. I just want to know, are these rates of change changing? Are they increasing or decreasing? And that's all I really need to know. They don't need to go any further than that here. We have plenty to think about in this assignment, so we're really not addressing those deeper concepts yet. Now, once they finish this task, we'll move on to our team task. Okay, so when we get to the team task, I highly recommend you begin the lesson, begin the class period with this task. So what I'm saying is you should be in day 2 at this point. And they should do this task on day 2. I would not try to do everything in one day. It says 1 to 2 days, but it's really 1.5 to 2 days is what I probably should say. So on day 2, they should start this task, and they definitely should work them in front of other classmates. So the way I would handle this team task is I would send teams to the board to work on this. I want them to draw a picture of the barn, show me where the X is, tell me how to find the areas, and we'll discuss that, or how to find the lengths and what are you doing. I do not give them the values for width, but they should try to type widths in this table so that they are equally spaced, or sort of equally spaced. I don't think you can get them exactly equally spaced. I think the last ordered pair I had to make it a little closer, but I think I got all of them equally spaced except for that last one. So what I'm trying to say is don't count by ones, count by something else. This one is also quite different because they cannot use just any width they want. They have a limited amount of space to use for the length of this rectangle, and so if they start at 0 for their width, they'll have 64 feet of fence, which goes way past the edge of that barn, which is only 40 feet. So they're going to have to think a little harder here about what numbers make sense in this context. And I want them to think about the context. Forget the algebra right now. Let's talk about real life. If you have 60 feet of fence and you know the length has to start at 40, it can't be any longer than that, then what's the smallest possible width you could have? So let them wrestle with that. Let them think about that. Don't tell them. This is part of what's, unfortunately, you got to kind of break them in, because kids are used to sitting and waiting for a teacher to do the work for them and to show them exactly how to do this problem. But I don't want to do that because they will not learn how to problem solve. And also, they won't really make sense of it until they kind of play with the numbers on their own and make sense of the numbers. So here we start with the numbers. Look at the numbers that are possible for widths and lengths, and we want to use all 64 feet. So how are we going to do that? Once they've completed their table, they should be able to see some kind of pattern in here and determine an equation for lengths as a function of width. And then they will write or type that into Desmos and make a graph and insert that. I am again going to make a video explaining how they can create the equation using the function and using x subscript 1. So if you've never done that, I did show it a long time ago, and it is in most of the Desmos calculator trainings for those state tests. So if you want to see that, it's repeated throughout those practice videos, but I do want to do one here because it's such an important skill, and I do show the kids that over and over during this part of the course because they're using it quite a bit. Mainly because these areas on the next screen are going to get really big. So we don't want them zooming in and out and making a disaster of their graph. We want a nice looking graph that they can read and comprehend and use to solve the problem. So the next question is, what's the domain in this context? Now we normally say anything greater than 0, but we've already talked about that. A width can't be like 5. It can't be 2. If you try to use an x value that's too small, there's going to be a lot of fence hanging over the side of the barn, and we're supposed to be using the side of the barn for one side of this rectangle, so we cannot go past the edge. So that's going to impact the domain. Another thing is, what types of numbers are we using? Counting numbers or real numbers? And why is that? So as the kids are working in their teams, these are the kinds of questions you come around and ask them. You know, what do you think the domain would be in this situation? How big a width is possible? How small of a width is possible? And how do you know that? Can I use fractions and decimals? Is it possible? Would I want to do that in this table though? Probably not. I'd probably want to use nice, pretty numbers because they're easier to work with. But have those conversations with your kids as they work in teams. Let's look at the last slide. This is the second part of their team task. Now they're doing the area and they're looking for the maximum possible area. So basically they'll take their widths they used on the previous screen and use them again here. They can copy and paste them, by the way, into this slide, but this stuff's probably going to be written up on the boards, which is where they should be working this, and then talk about these areas, what's happening. They'll create an equation and a graph and insert, and then they're looking for the maximum possible area for the rectangle that is enclosed. If they've spaced these numbers well, they may be able to figure it out just by looking at the data in the table. Like if they've gotten those widths counting by a nice number, they may actually run into that number. That would be awesome. But if not, they've got Desmos, so they can plug in values of x and look for some symmetry in there and see if they can find it. So this concludes our optimization lesson. We have one more lesson before we take our first test in term 4. Y'all have a great day.